things and I consider the environment, the light's not causing any harm. Either I've got organisms who they have sensors in their eyes to find even the tiniest amounts of light, or they have developed eyes that are barely functional or not functional at all. So the light isn't doing any harm or any damage. Now, obviously, if the organism is being eaten, that's a slightly different story, but we're no longer talking about the organism itself. So the reactants that are being put in, the products that are coming out, those are all things that are safe to the environment, whether it's the light or whatever happens to the oxygen. So there should be a pretty good connection for you there. So now, third, if I look over here at the different luciferin molecules, we talked about this a little bit as well, and I believe I have it in your life-friendly chemistry. There's a bit of notes in there too. We talked about how luciferin evolved over and over and over and over again, both in fish in general a specific amount of times and just in nature. So when I look at these, there's a couple of patterns that I see. So first thing, always, I'm going to go back to the operating conditions and I'm going to think about, well, what do I see? Why would I see certain patterns in one and not in others? I'm going to look for things that are in common. So first I'm going to kind of just go through the organisms and see what I have. Right, I've got firefly, that's terrestrial. I've got a snail, that's got a little bit closer of a link to my aquatic organisms. It's a gastropod, that's more related to the squishy cephalopods and all that stuff, but it's also terrestrial. Bacterial luciferin, okay, like those can be symbiotic and inside an organism, or they can be sort of free floating out in the open water. So this is also, like, one, it's not a multicellular organism, and two, it is more aquatic in most cases. Now, if I compare that to this one, coelenterozine, I see 1, 2, 3, 4, 5, at least 6 different major categories of organisms there. That tells me something a little bit different than when I look at the firefly here. Wow, that only applies to the firefly, and this one applies to all those different organisms. Like comb jellies aren't even jellyfish, and shrimp are completely different from fish. So like there's some similarities between these organisms in terms of common ancestor. But if you look at like a fish, which has an endoskeleton, completely different body form, and compared to some of these guys, either I have common factors of evolution, common pressures, obviously I have some of that, and I also have some common resources that make this molecule perhaps easier to synthesize or more likely to synthesize, or I have one common ancestor way, 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 way back in the past that synthesized this molecule and passed it on. It could be a little bit of both. So this one is really interesting to me because of the diversity of organisms that uses this particular luciferin. Again, luciferin is the sort of original molecule that the reaction sort of happens to. So that's the one that's changed. This is the one that your body might have to make again once you've done that reaction. You're going to have to make more luciferin. So that also will tie into one of your life's principles. And I think I mentioned that one in today's talk. Okay, now I've got dinoflagellates. Okay, so those are also single-celled. They've got a completely different environment from this guy. These tend to be mid to deep sea organisms. Some of them have sort of a vertical migration that happens, but for the most part, these are deep oceanic or mid-oceanic. My dinoflagellates, well, these guys are all happening right at the surface of the water, so I've got completely different operating conditions. One, what's happening with my nutrients is completely different. Here, I've got stuff, and here too as well. This one says super deep sea stuff. These two, it makes sense for these to have some common structures and as well as some common sort of ingredients that make them up. They are coming from very similar operating conditions, similar biomes. So that makes sense that they would have evolved similar luciferin molecules. However, for my dinoflagellate, again, I've got completely different resources. These deep sea things have a lot less nutrients to gather. There's marine snow, which is basically just decomposing stuff, and mucus nets that various other organisms have made. It's just stuff that's falling apart, and obviously we have some predation going on there, but there's just less overall stuff to build with. If I look at my dinoflagellates, well, where are they located? They're on the surface of the water. They don't really have much of a migration. However, these are found in every part of the ocean. We see them a lot of times on our coastlines. Why? Well, there's going to be a lot more, the heavier concentration of nutrients there, both from our runoff and some of our things, and as well as, the physical structure of the land is going to also sort of accumulate and sort of gather things in a higher concentration as the water hits up against the land. We've got dying organisms, all that stuff. These also have the ability to capture nutrients when we have storms, or if we have some sort of accident or whatever going on. That energy from a storm is going to mix up the surface of the water, providing more nutrients and resources to the dinoflagellates. Whereas this deep sea organism sort of stuff, those storms and hurricanes and whatever, those aren't going to have access the same way that these do. Similarly, my dinoflagellates, they've got chlorophyll in them, as we looked at earlier, which means they can take advantage of the sun, but that's a double-edged sword. Yes, they've got the sun as an energy source that can start that sort of reaction, but we know the sun also has UV rays, so there's also bombardments that can happen that can cause trouble with basically any molecular or cellular structure that we have. So it might make more sense that this is more complex. I've got more resources. It also ties in with the evolution when we compare it to chlorophyll, the resources that it's using in terms of energy with the sunlight, and so on. Again, when you think about the evolution perspective and you look at all this variation here, that should tell you a little bit about common ancestry and that sort of thing. Lastly, we talked about doing chemistry in water. Well, obviously, we've got the large-scale environment. Most of these are existing in an aquatic or a marine biome. But what's interesting there, again, from an evolutionary perspective, we see that almost all of these organisms, well, actually all of these organisms that are marine animals, are in ocean water. They're not in fresh water. That's something to think about, because that tells you something right there. Okay, so we've got the large-scale environment of the ocean in particular. But if we look at the organisms that are terrestrial, they're on land, terra meaning earth, we also see something to do about the water. If you are in an area where you see fireflies or snails, those are generally organisms you also see in higher humidity. So when I was growing up in the Midwest, we had fireflies all over the place. As you start to travel west, it gets more dry. By the time you get out to Denver, where I am now, there aren't any fireflies. So that's interesting. Snails don't have any sort of exoskeleton to speak of. We know that they are also very moist creatures and they use a lot of mucus. So if they were in a really dry environment, that's not going to work for them either. So there's something about water that's happening there externally. Lastly, we talked about the Myatoxia, which were the millipedes that glow, or we talked about the fungi that glow. Both of those organisms as well have higher concentrations of water in the air. Now, the Myatoxia, a little bit less. Those are found in the Sierra Nevadas of California. It's a little drier there, but again, they're kind of along with those decomposers. They're more in the soil. You're going to have more moisture. Similarly, with the fungi we looked at, one of which was in the Brazilian rainforest. They're in the understory. Again, water is a component. So that's sort of the external large-scale environment. We've got chemistry that somehow is happening in water. It's being kickstarted there. There is a factor. On a small scale, a more atomic, molecular, cellular scale, we've got chemistry in water. We know that that makes up the majority of our bodies, and especially if you look at some of these organisms as well, within their bodies themselves, they're high in fluids. I mean, you think about something like a jellyfish or a comb jelly, there's going to be a lot of water that's even just like making up their bodies. So those are all things to consider. I also put the life's principles down here so that you could connect to them. So all of those things should connect in some parts to the life-friendly chemistry. And then there's definitely several that I mentioned here that are either evolving to survive or adapting to conditions. Now, I want to just point out one thing about adapting conditions. I touched on this a little bit in last week's example. So just going into adapting to changing conditions, we talked about light being a factor. So if I think about my hatchet fish that had that counter illumination on the bottom, it can change if that's bright or dim. There's something to adapting right in there that relates to that. We also talked about the Bermuda worm, who a couple days after the full moon, it's going to go up to the surface and do its thing. It is also adapting to changing conditions. So sometimes those conditions are like a huge storm. Sometimes it's a change in weather. We talked about the storms and stuff in terms of the dinoflagellates here. Dinoflagellates was also really interesting and cool here. They will glow brighter after several sunny days. All right, we've got some taking advantage that actually gets into some of this stuff too. So think about if you're adapting to changing conditions. For these organisms, the amount of ambient light is definitely one of those things that's changing. That's not something we often think about. And if we do, we think about just day versus night. But that's not always true to these organisms, although in some cases it is. So there's just a little bit more information for you to hopefully help you both figure out your notes for today, your weekly assignment, and your mastery assignment. All that stuff goes together. We're just looking at different processes. Now, the last thing that I want to point out to you really quickly, let me go back into my mural here. This one. Okay, I'm going to go all the way back to this for just a second. When we talked about the city and the functions, so today what we were really getting into this week and last week was utilities and power. And specifically, if the light is the first thing to be knocked out, well, we know that there's going to have some impact here. Where we're going by the end of Saturday, since we're kind of finishing up with bioluminescence, is we're looking at this whole pattern that I mentioned earlier. So we've got the essential structure and service. That's the utilities in terms of power, electricity, and light. The structures that we have, well, in the beginning of the week, we talked about all the different structures that we have in our homes that make light, which ones are going to be knocked out by power initially, which ones are charged on batteries, what that sort of stuff looks like in terms of that structure. What are the functions? What do we do that stuff for? Now, if we looked at the champion organisms, they are potentially using their light to do different functions than we are. So there's something interesting for you to explore, our functions versus their functions. So we found our champion organisms. We've got a bunch of them that are deep sea, and then there's also some variety on land and what have you. Some are, again, right at the top of the ocean, like the dinoflagellates. So we've got some champions that are all doing some really cool stuff surrounding the adaptation of light. Now, by the end of Saturday's mastery, I'm asking you to think about the redesign. If we have a hurricane, we've got some giant awful storm that comes in, knocks out our power, now we don't have light. How could we consider what this organism does, the context this organism lives in, and apply some of its ideas to redesign what our structure of our light and what the function of our light might be? So that's what I want you to look at. I hope that helps. And I will see you guys soon.